It seems like most likely starting again in February. We'll get back to you with dates for that. So firstly, I wanted to see if anyone had anything that stuck out to them from last week. Last week we went through putting climate data inputs and a little bit what those data look like. There's a data format and the fact that you put in for specific station locations and the station data gets assigned to every unit in the model based on whatever station is closest. So we went through that, and then we looked through the long set of menus for input parameters for the model in the SWAT editor program. Just to give you an overview of the various menus and parameter input tables that are in the back end of the model that you can change and edit to meet your needs. From those topics, was there anything that stuck out to anyone they were surprised by or that they learned, or anything you wanted to share that just to cast our minds back to what we did last week? I guess my next question would be also, what have people been able to get their tutorial model to the point where you've hit run and it's run through the model? The model's done all the calculations. Were people able to get to that point? Welcome to just unmute and say things as well. People hear me? Was anybody able to run their model?
Hi, Julia.
Yeah, go ahead.
I actually did try to run the model on Sunday, but I didn't get time to finish. But I did follow the steps that you showed us. So even for your first response, for your first question, I think my takeaway from our last session is that I think we did discuss a little bit about the climate data, and even on our previous sessions in terms of, I think you said the model actually assigns the climate data using on the HRUs using the closest station. And my takeaway there was that looking at this bus climate network that we have in South Africa, I think it's one of the limitations in terms of the input data. And I wanted to find out in terms of other options, if we can blend satellite data with institute data, and what are the implications of that in terms of the accuracy of estimations and simulations. Thanks.
Great, thanks, Nando. That's a really good question. So yes, so the model is, the way the input is structured is to input for stations, but you can make up stations. It doesn't know if there's a station there or not. So what I've done in the past, so like if you have a gridded data product that comes from a satellite, for example, satellite data, and there are these blended products. Some of you might have heard of HydroNet. I know that uMngeni Water does have a subscription with the HydroNet project, and they make a blended product using, I think, radar and some other station data and satellite data as well. So there are other global products like that as well. So you can use those, and I think it is a good idea to use those given the sparse station network that Ntando was mentioning. So to use those, the way that the model interface is set up, and a lot of models are like this because they date back to times before we had all these satellite products, and they're now updating themselves. But the way that we do that here with SWAT would be you can make like a set of imaginary stations that are at any point you want. So it can be a grid of so what I think we'll probably do in this case is make a grid of imaginary stations that are at the points, the middle of the grid cells of the gridded data product. And then you assign a time series, the time series data to each one of those points, as though it were a station, but it's not really a station, but it's the center of a grid cell that has gridded product data. So, or you can make a point for every subcatchment or a point for an altitudinal zone. As long as you have data, like a rainfall time series and a temperature time series, and those time series data that you can assign to that point, you can put points wherever you like, even if there's not actually really in real life a station there, because we are making the inputs and we are putting them in. So it doesn't know if there's really a station there or not. So it's just a question of having data that you think represents the climate at that particular point and putting the point in with the time series data behind it. So that is what I recommend we would do in this case as well, given that, yeah, we don't have a great station distribution in the country. And actually South Africa is not doing too badly compared to a lot of other countries in the world. I know Europe has a lot of stations, but it's a densely populated continent, well, Eastern Europe. And but a lot of other parts and places in the world don't have too many more stations than we do. But it's not ideal. It would be better if we had more stations, and we used to have more stations operating than we do now. But yeah, so it is what it is, and hopefully we can improve that, but we can use these satellite products and input and find a way to input it into the model as though it was a station. Does that make sense in terms of how I've explained an approach for putting the data in from a satellite product or another product?
Yes, I think it does, but I also have another follow-up question.
Yes, go for it.
I think you at some point we had some discussions with Jason. I'm not sure if you were part of those discussions. And one of the questions was that there seems to be overestimation in terms of the satellite products that we currently use. So what is your take on that? We use it regardless of the overestimation, or with there are other methods that we can use to compensate for that overestimation.
Yeah, so there are methods. If you have some goods like stations you think are reliable, you can compare. There are methods to what they call it bias correct data, climate data from other products, and you often have to do that because there's a lot of assumptions being made in a lot of these satellite products. So that is something you can do. So I don't have a slide. It's a bit, I can talk through it in words quickly, but it's a good one. I'll make a note and we'll go through that in a session next year. Because I will show you like how I would suggest we do the inputs for the uMngeni water model. And so yeah, you can, if you had an idea, there's like what you call a systematic bias, like it's over predicting, or it could be over predicting the high events and under predicting the low events, or those kind of things. So you would look at the satellite data against some stations, and you can apply some correction factors. So when we say bias correcting, it's describing what the bias is. Is everything shifted up, or are the high events shifted up and the low events shifted down? Or sometimes the low events are too high and then the peak rainfall is okay, or too low. So you can shift things by percentiles. So you can match, like you can see how is you can look at how the percentiles map to each other. So that's essentially like comparing large events and small events and seeing how the satellite product is doing on the different side and mid-size events. And then you do a correction factor for different sizes of events. So like the 10th percentile event, the 20th percentile event, the 50th percentile event would be in the middle. So there are different bias correction techniques you can apply to try and make the satellite or blended product inputs more realistic in as much as we can. So it's always it's always a balance because these satellite products give you the spatial distribution in a more seamless way than the station data, but then they do have, then the magnitudes might be a bit off. So these are great questions. So these are things it's good to hear from you, and then I will make sure that we cover some more of that in our next sessions. Thanks, Nando. It doesn't sound like many people were able to get their demo model to run. I will, if somebody try, like, I think I did want to make some space for troubleshooting if people tried and gotten certain errors, because I can look at that. But if you're able to try, if you're able to catch up later, and if you have problems, you can send me screenshots if you have any troubleshooting you need me to help with, if you run into errors on the way. But I will move forward with that piece regardless, and then hopefully you can catch up at some point. Again, like, I'm happy for people to do this in groups. Not everybody needs to know how to do everything on the technical side. I think the biggest thing I want people to understand is sort of what is what inputs are going into the model, and how we're getting to those inputs, and what outputs are coming out, and what it's doing and what it's not doing in terms of understanding the outputs. I think it does help to see the software structure to give you a picture of that. And then some people are likely to are going to be working with the inputs and outputs directly as well. So what I wanted to go through, so we're still at the stage of going through how the software works. I am going to get into some of the model setup decisions in terms of land cover in the session today for the uMngeni water catchment areas, and give you some background of what's already there. Tobeka, I see you have your hand up. Please go ahead.
Oh, hi, Julie.
Hi, yes.
Okay, so the last tutorial or lecture, I didn't attend it, so I just attended the first part, but I'm sure you answered this question, but I just wanted to ask. So if rainfall and temperature come from two different nearest stations, does this affect model accuracy, or does it introduce some inconsistencies?
Yeah, so if they come from two different, so the model does look at, you can put things in from different stations because they understand that things are like different things get measured in different places. We often have more rain gauges maybe than we have full weather stations, for example. So it doesn't, it's ideal, the more data the better, obviously, but the model is most sensitive, it's always going to be most sensitive to rainfall. Rainfall is the biggest driver. And the way that temperature changes over the landscape, it can be, especially, okay, so you'll often hear that it's actually very important in Southern Africa and in Africa, and generally in the global south and around the equator, just in more semi-arid areas, because evapotranspiration is a much bigger part of the water balance than in colder parts of the world. So when you see literature that say rainfall is the biggest driving factor, it is, but it's also evapotranspiration in these areas is much bigger factor. So it is important to get that as right as we can, more so than it would be in a colder climate where that's less of a big flux. But it doesn't vary quite as much in space as rainfall can. And so it's, ideally we do want more temperature data, but we often don't have it. It won't be as big of a factor in the model accuracy or inaccuracy as the rainfall will. But we are going to use, there are satellite based products on temperature, wind, relative humidity, and solar radiation, and those are actually getting better. And the thing is, those tend to be actually a bit more accurate than the rainfall products because it's easier to estimate those things from satellite data, at least temperature, than it is to estimate rainfall from a satellite. Because the satellite rainfall, they're like, for the satellite products, a lot of them, they're looking at the cloud. The satellite looks at the rain cloud and then tries to judge from like the colors and the temperatures in the rain cloud how much is rain is falling out of it. And that's quite a hard thing to do. Whereas the temperature stuff, there are, I guess, and then there is an issue of cloud getting the temperature through the cloud of the temperature of the Earth's surface through the cloud. But it's if the satellite can see all the way to the Earth's surface, it's pretty good at getting temperature from infrared and other radiation sources. So temperature from other products tends to be not so bad. And then there are these things called reanalysis products that they actually look at a climate model. They take the satellite estimates and then they also apply a climate model to make sure things are consistent with one another. So humidity and temperature and wind and solar radiation are all linked to one another. The climate system is all linked to one another. So these reanalysis products, they bring the satellite products together and they adjust things so that it's like physically consistent. Those conditions could exist together the way that they do in the real world. And that's a mix of satellite data, station data, and some modeling to make these reanalysis products. So for temperature inputs and humidity and wind speed, actually, I would suggest that we would use a reanalysis product here, and also look at how it compares to station data. Sorry, that is a long-winded answer, but it was a very good question, and it's the climate data is really important. So we will go through the inputs for the uMngeni water model. And so again, if it's a gridded product, you can put like a regular or like a grid, a set of imaginary stations. I say imaginary stations. They're like points where we have data assigned to each point across the landscape based on the satellite product or the reanalysis product in this case. So we will come back to that, and it's a good question. A lot of these things we can get, and now Google Earth Engine makes things easier to access in terms of the data. There's other websites too, but they make it easier to download what you want for the areas you want it for. So what I'm hoping to go through today, we're going to go back to that tutorial and look at some of the outputs that SWAT produces and where they are and what they look like. And there's a section of the tutorial on going through some of the model's visualization tools that I think will just help you get a feel for what the outputs look like. And I'll show you the file structure and what that means. And then in the second half, I want to start looking at I know we started talking about climate, so maybe I should have gone there today, but I prepared to go through a bit more land cover, because the land cover question, I'd like people to do some thinking about it as you go through your day-to-day and the other work that you're doing in January. And then when we come back in February, we can see what we think about how to input the land cover for the uMngeni water models, catchment area models. So to quickly recap what we've done in that tutorial so far to show you how the model works, we've gone through these various steps that happen in QGIS, and those were inputting your digital elevation model, and you use that to delineate streams and channels, and then delineate catchments and subcatchments. And then within that, there was the landscape units, so a floodplain versus upslope areas. And then the HRUs, which was the combination of land cover, soil, slope, and then that landscape unit position, upslope, downslope, floodplain and upslope. And then that divided the landscape into hydrological response units. And for every one of those units within a subcatchment and within a landscape unit, the model will calculate the water balance, how much water it'll assign a rainfall and all the drivers of evapotranspiration, and then it will calculate for every day how much infiltration there was, how much runoff was produced, how much surface runoff, how much water ran, lateral runoff, so interflow through the soil, how much water gets stored in the soil, how much evapotranspiration occurs, how much percolation occurs into the groundwater aquifer. And then the aquifers are by landscape unit within subcatchments, and then how much water flows from the aquifer also to the stream. So that whole delineation and model structure setup happens in QGIS based on the inputs you give it. So the digital elevation model, the land cover map, the map of types that you want to represent, and the map of soil types you want to represent, and then if you want to do separate slope classes or not. And so we did that in QGIS, and then the software packages all that information about the structure of the model, and it passes it to that SWAT editor. And then in the SWAT editor is where you start putting the input values to things. So you give it the climate data there, and it'll assign it based on distance for whatever points you put in. So they're called stations in the model, but as I say, you can put any point you can put a time series to that point, you could input it. And then there's all the different parameter values about the land cover types, the soil types, the management of the land cover, so irrigation, fertilizer application, data about the soils that you may want to change, and then connections in the landscape as well. So how things flow from the upslope to the floodplain to the stream. So there's various aspects of that you could change if you want to. Some of it's worked out for you based on the topography, but if you find that it's not working the way you expect, then you can go in and manually change some of those variables. And then the groundwater variables. So there's various aspects of drainage of the aquifers that get assigned. So we went through where those parameter tables are in the interface through these drop-down menus and what some of them look like. As you saw, there are quite a lot of them. And as we go through the uMngeni water model setup, we'll get into particular ones that we'll want to change, because there are a lot. The model's not highly sensitive to all of them, it depends what you want to focus on and look at. And there are quite a lot of parameters to do with water quality. So how much nitrogen and phosphorus are in the soil, how much are getting applied, how much if the plant is a nitrogen fixer plant, the vegetation fixes nitrogen, those kinds of things that are relevant to the water quality aspect. And so we went through a bit of those menus last time. And then when you are happy with everything, you go to this play button here, and you can run your model, and then it will do all the calculations for the time period you've selected, and it'll save the outputs that you've selected into a database. So I'm going to go through what the file structure that it produces looks like and what that means for how we get to process the outputs and look at them. And then we'll look at some of the outputs, and SWAT has some existing tools that help you look at the outputs visually that are quite nice. And we'll have a look at those tools. And then we'll hopefully at that point, see where we get to, where we put in our break, but I'll definitely break around 10:30, and then we'll go into talking about the inputs for the uMngeni water catchment models. So first I'm going to talk through this file structure, and then I'm going to close my presentation and actually go through my directory and show you what all is in some of these folders. So when we started a model project, when we started a new model in QGIS, it asked for a name and which folder to put it in, and we put it in our QSWAT Plus projects folder. I accidentally made an extra folder, so mine is nested within two folders, but it's not a problem, but yeah, yours might not be nested the way mine ended up. But every time you make a SWAT Plus project, it will have a folder, and it'll have certain things in the folder that the software puts there for you already. And then you can put other things in, and we put some of the input data, example input data in it. So within a project folder, there's going to be your QGIS project file. So that's your QGIS project, obviously. And then the other things that the model software puts there for you are these databases. I don't know if anybody's worked with Microsoft Access as a database program. And other database programs are similar to spreadsheet programs. It's just that there are links between the different tables. So if you had a spreadsheet with lots of different sheets in it, and there was an ID number like for a stream, and you had, let's say you have a set of stream units with different ID numbers, and one sheet in your Excel table has lengths of the stream and channel sizes. And then your other table has information about nutrients and stuff. And both of those tables have the same like ID numbers and names for the stream. Those two tables are linked. They both have data about the same thing. And they have these ID numbers that are consistent between them. So database programs and database software are designed to do that, to keep track of linkages between your different tables, because each table can have data that's about the same, different data, but about the same elements. And so there are these ID numbers that link across tables. And it's quite useful when you have big sets of data and you have some information about some units and not information about other units, and then everything gets linked together with ID numbers in the back end, and you can make these summary tables that bring things together. So that's generally what databasing software is, and some of you might have used it before. So SWAT Plus uses a database, a freeware database program called SQLite in the back end. And so these are these database files that are SQLite software files, and they're database files. So when you make a new project, it makes this SWAT Plus datasets one that gets copied over, and that's the defaults that come with SWAT Plus. So we looked at, for example, there were all these inbuilt parameter values for different vegetation types that the model comes with. And those are all stored in there, and then the software accesses them. And then it makes another one that has the name of your project. So in my case, it says robot2 and .sqlite. That's essentially a copy of the default values. And then if I change anything in that SWAT editor interface, it will change it in my project version. So this one has the actual inputs for my project. This one has the SWAT defaults. And so it can refer back to them. So it makes these for you. You don't have to make them, but when you work with things in the SWAT editor, it's working with these files that are there, these database files. It also makes this watershed folder for you. And what's in there, I'll show it to you just now, but it has a folder for rasters and for shape files and for text files within that watershed. And this is about the model structure. So this is where the GIS files of the channels that we make, the subcatchments, the landscape units, the HRUs, shape the finalized versions of all of that spatial data that's in your GIS project for the SWAT Plus project end up in that watershed folder. And I'll go through, I'll open it up and show you the different files just now. But it also has copies of your DEM, your land use and your soils maps that all get aligned up by the model if they're not aligned already. And then it also makes this scenarios folder. And this is where the outputs of the model get stored. And inside that scenarios folder, there's a results folder and there's a text in out folder. And I'll go through what's in those as well. There's another database file, and then there's shape files that get used for the results as well. And then the text in out has text file versions of all the model inputs and outputs that are also in these database versions. And part of this is historical from how the software was structured. It used to, instead of using the databases, it used to use text files. but it can be easier to interact with these text files sometimes than with the database program, or I find it easier. So, and different users, depending on what software you're comfortable with. So they've left both options for you. And then this project folder can have anything else we put in there. We caught in the tutorial, as we've done it, we copied over our input data from the examples, pre-prepared input data. So the soils, robot streams, observed main outlet point, land use DEM, and the climate data, we copied all of that over from the examples data folder. So we put those in there, but the things with the blue arrows are the things that the model, and we put in these soil tables and land use tables. But these things I have the arrows next to are what the model makes for you when you set up a model. Inside that scenarios folder, this is where the results end up. There are two folders there. One is results, and one is this text files for inputs and outputs, text in, out. And the results folder will have a database with all the outputs. Oops, pardon me. I see I wrote that wrong. I wrote SWAT. It should be SWAT plus there. But I'll show you that just now, and then these text files. And so to understand the text in out files and also the database files, there are a lot of tables of inputs and outputs. And to understand what the file names mean and find the information you might be looking for, the website is very helpful. So we'll jump back and forth to there. So this is an example page from the website about the water balance tables that the model outputs. They're flagged with a WB. So when it says basin WB day, that's daily water balances for the entire basin at once. So the basin is the entire model area. And then this one, HRU WB day, that's the water balance of every individual HRU on a daily time step. And then HRU WB MON would be the water balance for an HRU on a monthly time step. And then there's year, and the AA is annual average. And so it'll make these depending on what you decided to save. When we ran the model, and last week we decided to save different elements of the water balance and the nutrients on either a daily basis, a monthly basis, a yearly basis, annual, and then annual averages. So it'll make all these tables as your outputs, and then there are nutrient balance tables. There's tables about losses, soils, etc. So this part of the website that has SWAT output files tells you where the file names that, and gives you some information about the naming conventions of these file names. These are the file names in the text in out folder, but they're also the like spreadsheet sheet names in the database as well. So what all of this means, we've got storage of outputs as in a database file and storage of outputs in separate text files. What this means about how we look at the outputs, there are these inbuilt software tools that we're going to go through now for the tutorial that help you interact with these outputs. You can assign results values to your shape files and make maps, and you can make graphs with these visualization tools, and you can also make animations, which is quite cool, where it shows you how things change over time by landscape unit or by subcatchment, etc. So what's nice about these inbuilt tools is that the process for viewing some of the outputs is already automated. You need to go through some menus to get there, but the process is laid out in the software. The drawbacks of looking at our outputs that way is that if you want to look at lots of different outputs and combine them in certain ways, it's not very efficient for doing that. If you're rerunning the model over and over and you're rechecking things, to try and improve it and stuff. It's not as efficient as coding, which I'll get to. Another option would be to output some of the time series data into an Excel format from these database files. And then if you wanted to show it in a map format, you would then need to manually link things. The advantage of that, I suppose, is that if Excel is what you're familiar with and you want to make certain graphs and you know how to make them in Excel and make them look the way you want them to, and so, there's user familiarity and control there. That's also really not very efficient if you're going to be doing it many times over and over and repeating it as you improve the model. The way that I work with the model outputs is to actually write code that grabs the different text file outputs from that text in out folder that we want to analyze, and then make whatever graphs and maps, and also grab the shape files that you want, and then you can make whatever graphs or maps through coded instructions. And that's much more efficient in terms of you don't have to work your way through menus every time. You write your recipe, your code of what you want it to do, and you can rerun it quickly as many times as you want to pull out your statistics and your graphs and your maps the way you want them. It does require some level of comfort with coding. Obviously, there's a lot of AI tools that help with writing code these days, which is great. You do need to have a bit of understanding of what's going on with the code, because it doesn't always do exactly what you've asked it to, or there are errors, etc. And you have to know whether it's made a mistake to some degree. But it's way easier than it used to be, and you don't need to know how to write so much code from scratch anymore. But I will be working with you on these. I'll be working to develop codes that give out specific output statistics that uMngeni Water is interested in for this model. And then you would have those codes to rerun it as you want, but it would help that some people understand them so you can modify them going forward the way you might want to. So there's different ways you can interact with the outputs from the model. I'm gonna switch over to showing you those folders again. Let me escape out of my presentation here and jump to this menu. Okay, so people who are able to follow along a little bit, you can go ahead and open your QGIS project. And then there's the SWAT plugin here that opens. Give me a sec. So to jump back in, this is where we did all of these steps. We delineated watershed, we created HRUs. We clicked here on this edit inputs and run SWAT plus, and that takes us over to the SWAT plus editor folder, software. And it takes us over to the SWAT plus editor software. And then we're going to come back here and visualize. But before we go there, I want to just show you those folders that I was talking about. So in my QSWAT plus projects folder, and then my project folder for this demo, our tutorial, this is what I was showing before. We have our watershed folder that the model makes for the software makes for us. And in here, there are folders for rasters. So this has the DEM, the landscape units as a raster. So that's that floodplain, the different versions that we tried in terms of delineating a floodplain versus an upslope area. Those get stored here in watershed rasters landscape if you need them for anything else. Then there's land use. So here it makes a copy of our input. We told it we wanted land use. We input this as the land use map that we wanted to use. And when we did that and finalized it, it made a copy that's aligned and clipped to the catchment area that's here. So it is another copy of it that the software itself stores here, so that it knows it needs to put everything where it knows how to find it. So it puts a copy of it clipped to our catchment area in here and aligned to the DEM. So in our project, we have this file here that has, and it colors it by, it assigns the names from the linking table that we had in our project, and it does that for you. And it puts a copy in here. In the shapes folder is where your streamlines are, your HRUs, and it has different versions of the HRUs, the full one and the actual one, because we did some lumping. And so it tells you the actual one is HRUs 2, and the full one is HRUs 1. So you'll see HRUs 1 here and HRUs 2. So when it runs the model, it'll use HRUs 2, the sizes and numbering of them and information about them that considers the lumping, the spatial lumping that we did. Similar for landscape units. And it's got, if you had reservoirs, this is an empty
Sonia?
file suite. Hi, yes.
Oh,
Yes.
sorry.
Oh, no. And the river reaches shapefile that it makes, or the channel shapefile, the subcatchments. So all the shapefiles are here that it makes. And then these text files are those reports that we saw that show you how much of the catchment has different land covers in terms of area and percent, and how that breaks down by our subbasins or subcatchments, percentage wise. And it also has by how many HRUs you have of different types. And then I think this is topo report. This will be, yeah, elevation bands. So it makes those automatically when you set up your model structure, and that's where everything's stored in case you were to need any of those. And then the modeling software, when it runs and when it pulls everything over into the SWAT editor, it knows where everything it is. It requires this file structure. Then once you've run your model, you'll have this scenarios folder. And we haven't named any particular scenarios. So if we did it, so it just starts with default, and you don't need to name and save separate scenarios if you don't want to. But if you ran it and then you changed the model, you would save, it would ask you, do you want to save it with a different scenario name? And you might say yes, and you'd give it a new name, and it would make a new folder like scenario 1, scenario 2, whatever you name them. It will make folders for each scenario that you make within this scenarios folder, and the outputs of the model run will be there. So ours is just called default for now. And then if we were to change something and rerun without saving it as a separate scenario, it will overwrite this with the new results of the new run. Every time you run it without renaming the scenario, it will overwrite it. So in here, as I mentioned before, there's a results folder and a text in out folder. Inside this results folder are actually shape files, and this will make sense. These are copies of the shape files of the HRUs and the rivers and the subcatchments and the aquifers. And there's also a folder for plots in case we save graphs in the visualization tool, and animations in case we save animations. There's nothing in here now because we haven't made it. It just makes this file structure for you. But it makes copies of these because, as you'll see, we can assign results. It can save the results of the output model outputs for each subcatchment and assign it in the attribute table, so that you can make a map of how much runoff each subcatchment produces, for example, or how much nitrogen runs off of different subcatchments, and you can make a map of which one is higher and which one's lower. So it makes a copy here that it can attach the results to make maps. And then it also has this database file. So this is the database file of the outputs of our model run. So I'm just going to double click on it to open it. So this is one place where it stores all the output data of the model run. It takes a sec to open. So this will have data once you have successfully run your model. So it has all of these tables, all of these table names. So let's pick one that might not have so much data that we could even look at basin. So if we look at basin, did we say the water balance year, for example? So that's, if I click on that, if I double click on it, in this is SQLite, that database software that I mentioned. So it's essentially, it's like a spreadsheet program, but things are linked by ID numbers across tables. So when you double click on one of these tables, it will show you, there are these different tabs. This is structure. So this tells you what all the headings, what headings there are in the data and what data type is in an integer or a real, like a decimal place number. But to see the actual data, you would go to this data tab. So here, I clicked on basin. So this is the entire basin. You can see the year 93 through 2000. And then you can see the data. So 93, it has precipitation over, this is spatially average precipitation over the whole catchment area for that year. And then you can see these different codes. So this is surface flow, lateral flow, water yield, percolation, evapotranspiration, summed for the year. So you have these different fields for the water balance. And to see what the website will help us with what these are. Do I have it open here? So if I were to go to, if I want to double check what all of these headings mean, I can go to that website. I've been giving you the SWAT Plus documentation. And if I go to output files and I'm looking at a water balance here, it tells me all the water balance table and file names, and then it tells me what the fields are. So Q, I don't know if you guys have, you probably come up with this back at university days. Q gets used as a shorthand for runoff or flow. So Q general, this is generated surface runoff that comes off of the catchment area, but some of it gets lost, might get lost on the way to the stream if there's diversions, etc. But this is the amount, that's why it says generated surface runoff before any other losses occur, or even evaporation in the stream or evaporation in the reservoir, etc. But this is the surface runoff that's generated from the landscape. This is lateral flow, so that's flow in SWAT terminology, that's flow through the soil that then makes it to the stream. And that's water yield, so that would be a sum across these, and then minus any losses on the way. Percolation, that's movement down through the soil into the groundwater in SWAT terminology. There's actual evapotranspiration, canopy evaporation, which is not modeled in every setup, and then plant transpiration, soil evaporation, these are components of ET. Then contributing surface runoff. Okay, so I'm not sure why they spaced them out, but that would be minus some losses. And then initial soil water content, final soil water content, average. So these are all the different components of the water balance table. They alphabetized them. No, they haven't. I'm not sure why some of this ordering doesn't make such great sense to me, but you can see what the different fields mean in this table. Run on would be if you had runoff through the boundaries, so we don't have that issue. But there's all these different, the different fields that are in this table are given here, and then it gives you the units that everything is in. So you can see these water balance are given in units, millimeters. So that's going to be millimeters over the entire catchment area. So if you remember back to those of you who've done more hydrology work, when you can have outputs in millimeters, and then you have to convert the units if you want to get to volume. If you're trying to get to cubic meters of water, you would have to multiply the depth of water over the area of the catchment to get to cubic meters of water. So these outputs are all in millimeters, but what's nice when you have everything in millimeters, the water balance balances in terms of inputs and outputs at this scale, because you don't usually measure evapotranspiration, in cubic meters of water. It's you could convert it there, but and then rainfall is usually measured in millimeters as well. So that's why they keep everything in millimeters, including the surface runoff and the runoff that meets the channel in this version of the table, so that you can do the math to make it balance, or to check the balance, I should say. So some of the so that's these water balance tables will have this for each HRU that you decided to save. If we save for, okay, yeah, we save the HRU data monthly. We didn't save it daily, so you don't see the daily table here. But if I double click on it there, and I go to data, it takes a little while to load because there's lots of HRUs, and it has for every HRU for every day. So it has the HRU name, or it's, in this case, sorry, for every month. So this is month 1 of 1993 for every HRU. So you can see each HRU number on month 1. And now there's 158 HRUs in my model after we did some lumping, etc. So each one of them, and then the rainfall was uniform in this example. Each one of them got 5.5 mils of rainfall in month 1. Looks like it didn't rain at all in month 2, because precip is 0. And then it rained 11 millimeters in month 3, and they all got the same. But they wouldn't have had the same. They all have different lateral flows and ET because they have different vegetation on them. So this is one place where all the outputs we saved are all in this one database file that's stored in that results folder. There are also these nutrient balance tables, and one there. This is by HRU, and then I just opened the yearly one. And you can see there was no fertilizer applied, etc. And then if you went to the website, you can see what's in the table. So the nutrient balance tables have this NB flag for nutrient balance, and then day, month, year, annual average is AA. And then you can see what all the fields mean. Again, are here. You've got like fertilizer, nitrogen applied to the soil, kilograms per hectare. You can see what the units are, and then you can work with them from there. And you could save this data. I think it's export. Yeah, you can export tables to Excel from here. Print data, import, export table. So I can export table to, okay, yeah, it'll export it to a comma separated value. Okay, it'll export it to a text file, a CSV. Okay, CSV. Okay, so you would export it as a comma separated value. And then you could open that up in Excel if you wanted to work with this data in Excel instead of in here, which you might want. I think you can build graphs and stuff in here, but it's a whole new software to learn. So that's why there's also the inbuilt tools in SWAT. But you could save any particular table that you wanted to Excel and build graphs and anything there that you wanted to. So this is this database file. And again, it's located in the results folder of the scenario, and it's called SWAT plus _ output. And it's always going to be called that. You can go in and change what this is called in your model setup, but I wouldn't bother. It's going to be inside your results folder called this. I'm gonna close it for now. So that's what's in the results folder. In this text in out folder, that's also in our scenarios default. In the text in out folder, there are those saying you'll start to recognize these names again. They're text files for each one of those tables in the database. So it's just the same, it's the same information stored in a different format. So there's the channel, there's the basin ones, there's channel ones, there's HRU level ones, there's LSU level ones, there's the NB is the nutrient balance, and then the WB is the water balance. PW is plant water. If I go to the website, I can show you the different ones. So these tables are the same. I'll open some of them for you now. So in this website, you can see so that you get water balance tables, there's nutrients balance tables, they say NB, losses as LS, and that's generally for, you can see what's there. It's losses is a bit of an interesting terminology, but it just means like input minus output, like what's removed off of the landscape. So they have nitrogen transported in surface runoff, for example, ends up in that table. Nitrogen transported in lateral flow. So I guess it's nutrient losses off of the landscape. Phosphorus sediment transported off of the landscape are in those. Plant and weather, sorry. Plant and weather are the PW tables, and what's in the PW tables, there's leaf area index, plant biomass, the yield, if you have crops and you've set up a crop rotation, and you might want to look at kilograms of harvested biomass. There's the weather data that's then averaged by, or you could see what was applied for that HRU, and you can see how the vegetation responded. It's helpful to have the climate data alongside the plant data because you can see how your vegetation ended up responding to high and low temperatures according to the growth curve that you set up in the model. Is it doing what you wanted it to? And then there are things like plant uptake of phosphorus, plant uptake of nitrogen, and plant carbon growth, biomass growth. So those are in the PW tables that are output. Okay. And then there's tables that are about the channel units. So that would be like your flow in and flow out of each channel unit. So that's what you want to look at for stream flow. SD, they all say SD, I'm not sure. I think that's a holdover from modeling sediment, I guess. So there's SD, so there's like the water balance of the channel, the precipitation, the evaporation from the channel surface. There's the nitrogen, the carbon, ammonia, etc. that's in the channel, how much water is stored in the channel. So these are all the output variables you can get as a time series for the channel. So if I was showing you things within that database file, everything is also in these text files as well. So I'll just show you a channel table, for example. So you will have the tables that you decided to save when you set up your model run. So if I wanted to look at, I'll open a monthly one, or let me open a yearly one so it's not so big. Okay, so because it's yearly, it has, these are the channel numbers, and these would link back to your GIS. And you can see there are 27 of them. And so these are the values for 1993 for each one. And there's the area, the precipitation. And now because we're looking at a channel, now the units are different. These are cubic meters of water because it's not on a landscape area, it's within a channel. So you have water stored, but there'll be flow. stored. Okay, yeah, then you get into in and out. So it's quite a big table. There's like nitrate in. So that would be the nitrates coming, if I go to a QGIS project, if I choose a channel like this one, you'd have your flow in at the top and your flow out at the bottom of the unit. So it'll have a value for what's coming in and a value of what's coming out. And then there's processes happening along the way that it's modeling. So like sediment, we talked about that before. Sediment can settle, nutrients can change form, things can degrade if you're doing, and bacteria could grow or die depending on the temperature, etc. So you have these in, that's ammonia in, nitrogen, nitrate in, and then and flow, and then you can go along in the table and you have out, and you have flow out, and that's out at the end of the channel unit. Sediment out, organic and out. So if you wanted to look at what's happening at the end of this channel, you would look at the outs rather than the ins, and water temperature. So when you run the model, it produces all this data for each channel unit, each HRU, each subcatchment, each landscape unit. It'll sum things up for you and produce these tables. Is that making sense to people? Do people have questions about how this is working or how this is structured so far? I see a thumbs up. Okay, cool. So yeah, so you can see there's lots of outputs that it saves because it's saving things by every unit and every time step and all the different variables that we've asked it to save. So we have the text in out version and the database version. And as I mentioned before, we can interact, we can make our plots, etc. from these different formats, or as the tutorial guides us, there's some inbuilt tools that help us make plots and maps we might want to make. And so we'll do that the way that the tutorial has laid out, just to show you what it can do. As I say, when you're doing a lot, if you want to do a lot of them repeatedly over and over, I would suggest coding for it. But we'll go through the tutorial so you can see what the outputs get a feel for what kind of plots you can make. And it is a nice way to do it quickly when you're starting out and getting a feel for the outputs. But now you know where they are. I'm going to switch gears over to that tutorial PDF. I just wanted to show you the backend file structure. So if you haven't already, if you're wanting to follow along, do go ahead and open your QGIS project and then you open the SWAT Plus plugin and you'll get this window like this. And I'll just to show you again, I will click. So we did our delineate watershed, create HRUs, and if you click on this step 3, it's gonna open up SWAT editor, where we added our climate and parameters and we ran the model. So I'm not gonna do much, but I just want to show you how moving back and forth between them. So it's opening SWAT editor. Takes a moment. It's going to ask me if I've changed anything in my model setup, if I want to re-import. So it says, have I done it? Have I changed? I could change the delineation. I could put in a new land cover map and redo the HRUs with a new land cover map. And if I wanted to save over my project, then I would import it again, I could import it with a new name as well if I wanted to. But I haven't changed anything, so I say continue to editor. And I can see when I go to the editor that it's already been run. It reminds me of that. So I've already run the model, and it's already imported the outputs into the database for analysis. So that was making that database file that I showed you with all those output tables wrapped up into that one database file. So that's what it means when it says imported output into a database for analysis. Because then it lets you, the visualized tools that we're going to look at now, use that database file. So last time we went through these, looking at all these different parameter tables that one could edit and inputting the climate data. And after you're happy with the way that is, then you would go here to run it, and we ran it already. So I'm not going to rerun it, but you set your period, your simulation period, and if you have a warm-up time. So we did 1990 to 2000, so that's 10 years. And elsewhere we did set a warm-up period. Is it not here? More advanced? No, that's daily time step. We set the warm-up. I'm not going to go back, but it's in the previous video. I thought we'd put it there, but it's actually elsewhere in the setup. And then we looked at what inputs, we chose which outputs to print. And by print, they mean save those files that we just looked at now. And which ones to save daily, monthly, yearly. If you have loads and loads and loads of HRUs, you generally don't want to save all the HRU outputs daily, because the file becomes too big to open. Except, oh, here's where the warm-up period is. Okay. Warm-up period is, it essentially means, because we don't know the groundwater table on the starting day, the nutrient composition on the starting day, the soil, like the soil moisture on the starting day, run for 3 years before we start even looking at the outputs, because we expect those first 3 years to be a bit off. So then it'll start counting from 93 instead of 1990, or the outputs will be presented. As you saw when we opened those files, it started at 1993, and that's why, because we put this warm-up period here. Okay, yeah, because it is running the model for 1990 to 2000, but it's only printing the output, the model outputs from after it's that warm-up period. And then it shows all these various tables we could save. So I'm going to just exit here, because I already ran, I don't want to rerun again in this demo, just because of time. But if once you were happy here, you could do save settings and run selected. And then after it runs, you don't need to do anything further. You could start saving things as scenario names, but you don't have to bother for this tutorial. Once you run, it'll prompt if you want to do that or not. But if you don't, you could just leave it as the default for now and exit. So I'll say exit SWAT editor. And then, oops. Oh, why it kicked me back there. But I'll just close project to leave. I'll say yes. So I close it. I must have opened it multiple times by accident in the background. Okay. So if I close SWAT editor after I've run the model, this visualize step will become available to me because I've done a model run. You won't be able to click on this one until you've done the model run. So the visualize tools are back in the QGIS space because it includes making maps of the outputs, which is nice. So if I go ahead and click on visualize, it opens up this visualize window here. And I will show you also on where we are on that. We're starting that section 7 in the tutorial PDF. Let me just pull it up here so you can see it. So, oops. So running the SWAT Plus model was 6.3.4, and it shows you that the data, the outputs are being stored in that database within the results folder. And then we're going to exit SWAT editor, go back to our QGIS environment, and go onto visualize. And so we're here at 7.1 now. Just gonna get that out of the way so that I can have my screen. All right, so when you go to the visualize results, there's different things you can do. There's static maps, there's animated maps, there's plots, so that's just graphs. And then this is some particular statistics you can do around environmental flows that they're typical statistics that the US calculates. They're a bit different to ones that we calculate, but they're quite interesting. I'm not going to go through these, but this is later on in the tutorial. You could always look at it yourself later if you want to. But we'll go through what's in the tutorial for some of the steps. So we're going to start with visualizing some static maps. And so you have to tell it, so if we had multiple scenarios, you would have, there would be a drop down here, but there's only the default one scenario here because we've only run it once. I'm getting that. My window's back to the front. All right. So then we have these tables again. So these names have come up again. These are the output tables. So you can map anything from any one of those tables that you want to at the unit that it's, so that you can map things by channel. You can map like the flow in different channels. It'll color the channels different colors based on the flow, or the nitrogen concentration by different channels. There's HRUs. You could color them differently based on, their runoff generation. Similarly with at the level of landscape units, or do they have the subcatchments? So it has all these different tables. These are things we've saved that it can make maps of. Okay, so it has LSUs rather than the subcatchments. That might have been a factor of what we saved. And then there's aquifers as well. So they suggest in the tutorial to do LS unit. Okay, for this first example, they say use LS unit PW monthly. So that's landscape unit, plant and weather monthly. Oh, but we only saved it. Oh, there it is, monthly. There we go. So the LS unit PW monthly. So that this website will show you what's in plant and weather table has things like leaf area index, biomass, and stuff. So I think that in the demo they're having us plot some things about the vegetation. We can come back and do other ones after, but this is just a general demo. And so that it's brought in that table, and it's going to make a shapefile that it's going to make a shapefile here in that results scenarios default results folder .shp. So the shapefile it's going to make when we go through this process is going to have the same name as the table and then results at the end. And that's a fine name. You could choose another name for it, but the default name does, once you understand what the names mean, it's quite a reasonable name, I think. You can choose to add, and then what you're doing here, you're choosing variables that it will add to the attribute table of this shapefile. So it's going to be the landscape unit shapefile, but the attribute table will have the monthly results for any or all of these variables that you want. So you could just, if you want to keep it clean, you could just add certain ones that you want, like you can add LAI, and you could add like percent nitrogen if you just wanted those two. If you think you might want all of them, or just, just in case you want all of them, so you don't need to make a new shapefile if you decide you want to add another one. They suggest in the tutorial you could just say all. So if I say all the variables that are in the plant weather table for the landscape unit monthly are added. And then you can choose how you want the data to be summarized. Total, daily means, monthly means, the annual means, the minimum or the maximum. I think you can only choose one option here. So they suggest, oh yeah, because it's or the data is already monthly, we could leave it as totals. I think they, oh yeah, okay. Just going down through the tutorial, make sure we choose the, okay, they suggest doing monthly mean, okay, that makes sense. So monthly means will be, if you do monthly means, it's gonna be like the mean for January, the mean for February, all the Februaries in the simulation, all the Januaries in the simulation. So that makes sense. So totals in this instance it'll take the total of all the monthly data, which doesn't make a whole lot of sense in this instance. So monthly means makes more sense. So it's not going to assign, because we've got, you have 12 months for the 7 years we're looking at. So it won't assign every value for every month for every year in the simulation to the shapefile. That will end up getting too huge of an attribute table for what, and you wouldn't want to, it'd be tricky to plot it that way, but we can animate it that way. So monthly means for the monthly data makes sense. So what it's going to do, I'll see what it looks like once you do it. So then you would pick monthly means here. And then we can click create, and then it's going to add this data to the shapefile. Oh, variable before display. So, okay, in addition, it's going to make that shapefile with all of that attributes, all those in the attribute table. But if I pick, they're suggesting biomass as something to display. So the one that you need to highlight one out of this that it's going to display, and it's also going to make a map in your project, or it's going to make a version of the shapefile that's visualized in your QGIS project. And it's in landscape. Okay, and you can check how many maps you want to do at once, but let's stick to one for now. And so if I do create. Okay, so now it's created. What has it actually done? So this is quite nice. So it's created a biomass default. It refers to the scenario. It's the default scenario, monthly means of biomass. And so if I open the attribute table, what does it look like? Okay, so it has the mean monthly value. Okay, so it's not January, February, it's the mean of each, it's the monthly mean. So it's kilograms. If I go to here, I could check biomasses in kilograms per hectare per month in this case. So it's the mean monthly kilograms per hectare over the time period is selected. You could also select a different time period if you want up here to do this monthly mean for. Okay, so excuse me, forget what I said about January, February, March. It's per month over any month, all months. And so our attribute table of this shapefile of the landscape units now has mean monthly LAI, mean monthly biomass, mean monthly crop yield, mean monthly crop residue applied, mean monthly soil temperature, all of the things that are in that plant water table. The mean monthly value has now been added to this shapefile that has this name and is stored in our results folder here. So if I go to our results folder now, it's going to have, here's the file we just created. So it's a version of our landscape unit map that has all of that attribute table, the monthly results for the plant weather table. And we could display different things. It automatically makes a coloring for you for whichever one you picked here. But if you want to do other ones, like we can change what gets displayed in the normal GIS way, or we can make a copy of it and make another one. So we could change how many classes and what color, etc. But it does an automatic one for you using a color ramp and some formatting that they SWAT people set up for you that with 5 classes using the natural breaks coloring. And so you can go in and change that as you like, make whatever maps you like, but it's fairly nice to look at it quickly. So you can see these landscape units obviously have way more biomass and these ones have less, and you could look at why, what of the inputs is different vegetation types, different soils, is resulting in a lot more biomass over here. It wouldn't be rainfall in this instance because we applied the same climate to the whole area. So it's most likely to do with soils in this case, or slope, well, a mixture, sorry, of, yeah, soils and because there weren't so many different vegetation types. So it might have to do with soils and slope, and not sure what else would have varied in this case. That would make it so different, but you would then think about that and look at what's there and why it might be different. And it could also be the way that the landscape is rooted. So, oh, I think there was some forest there. So yeah, then if you want to investigate why, which I always like to say, why does it look like that? It's probably to do with, yeah, okay, so there is these yellow ones, these are pasture. Okay, so it might have to do with where the pasture is. Or the forest, and then because the soil was kind of all the same, yeah. So there is more pasture over there in particular, over there. And then if I turn this on, where the pasture is, yeah, it's where the pastures have higher biomass. So the pasture has higher biomass because it's then summing it by the landscape unit. So that's one example of making a map using the tools in the visualize tools. If we want to make another one, for example, so we've just gone through in the tutorial, we've just done, what is it, 7.3. The tutorial has some other steps about combining, doing some math to combine results, like doing one result minus another result, etc., in QGIS or in the database format. And I find that a bit clunky, and I would do it with code myself. So I am gonna skip that part, but what I will show you is making some maps of channel variables as an example that they do in that that section. So if we wanted to look at another, let's look at channel, we can look at the flow out of some channels, for example. Let's look at the table. I think it's channel SD morph year. What does that have? You can always check. Oh yeah, this has flow in and flow out. It'll make this table, when you change the table here, you can always see what variables are there, or you go back to that website I showed you. So this is now by year, flow in and flow out. So if I add all the if I add all of them, just in case, all this does is it adds it to the table of this shapefile it's going to make. So it's going to make a copy of my channel's shapefile with all of this data summarized how I want it. Now this is annual data, so it doesn't make sense to have a monthly mean. You could do an annual mean, which I think, oh yeah, it doesn't, the annual mean makes sense. Let me just double check SD more. channel. The flow in, flow out is in meters cubed. So if I did a total, it would be the total for the whole simulation, or it'll be an average, this will average annual cubic meters is going to be what the data will be if we put annual means here. This would be the highest flow year or the lowest flow year if we did maxima or minima. But let's do annual means then. Total would be the total over the all of these years. So we'll do annual means. And then to do our first, to the way that it's going to add it to our GIS project, let's do flow out and create. So now it's added. It's made a copy of the channel shape file that has all this data, the annual means of all these values added to the attribute table, as we showed before. So what's quite nice here, and then you can see this is cubic meters. This is quite a low flow river then, but yeah, 0.3 cubic meters average flow. So you can see, as you would expect, the flow gets higher and higher as you go down, but you can see where it jumps and where it doesn't. So does that make sense as ways of visualizing some of the data? You can play around and make any maps that you want out of any of these tables, out of any of these outputs. And you can also summarize by different years. If you did it by different years, you would want to give it a name over here that reflects the years you're including so you can remember what you've done, because it won't be stored anywhere else. Like the attribute table won't, it doesn't mention the years. So you'd have to give it a name somewhere so you remember that you did a subset of the years. But you could do that and compare it. And actually, if you change this also, if you want to make different versions that use different statistics, you would probably want to rename these so that you can keep track of what you've done, and then you would save it, and then you can play around with your maps, make any maps you would like. Does anybody have any questions about that part? Is it making sense? Let's see, anybody have any hands up? So we've reached 10:30, so I think it's a good time to take a break. And then we'll come back and we can look at animations and graph plots quickly. And then we'll get on to talking about land cover for the uMngeni water modeling. Everyone all right? If we take a break, it's just 10:30. Let's come back at, I'll give us a full 15 minutes. So what's 10:48? To be exact about it. Is that all right with everyone?
Sure.
Good? Okay, thanks. I'm gonna mute and stop sharing for a bit. And I will see you then. I'll put that in the chat. Pause. Hi, everyone. Don't know if people are coming back. I'll give people a few minutes or a minute or two. You can just do a thumbs up or something when you're back. Nintendo. Oh, cool. People are back. Thanks. I will start sharing my screen again. And start doing Zoom the recording again. Right. Hi, everyone. I hope you had a bit of a stretch to come back to where we were looking at how to visualize some of that model outputs using the visualize tool that SWAT Plus software comes with in the QGIS plugin part of the tool. And we looked at a monthly mean variable for vegetation assigned by landscape unit. We've done one where we looked at a channel output value, so it assigns the values by each channel unit. This one's flow out. And we could display any other ones we wanted to. And just to recap this process, it makes a new copy of the shapefile saved with the name that you give it here. And then it also adds that shapefile to your project, and it does a coloring and display using whichever variable you highlight in this box here when you click create. There's also a tool to print as they print outputs. That would be to make maps that you want to save as a JPEG file, I think, or does it a PNG file, or and it helps you do that as well. I'm not going to go through that too much, but I'll show you. So you can do number of maps down here. Just because you may want to do this for reports, but I find that doing it on my own separately outside of this tool lets me do what I want to do more specifically. But it does help if you just need a quick output, I suppose. So that's 7.4. So we skipped some steps in the tutorial document that show you. They talk about calculating different outputs that are combinations of the ones that the model saves already. And as I mentioned, I think it's a lot faster to do something like that in a coding environment, and I don't think we'll end up doing it in this GIS environment much. The reason why I think it is worthwhile going through this tool is because it can help you, then you can keep going playing with this example model and looking at the kinds of outputs it produces using this tool to get an idea of what it is we should, like what formats would be nice to output things for the uMngeni water model that would be helpful for things you will need to do in your data in various management questions or other things you're working on. You know, do you want to show nitrogen, average nitrogen by stream channel in a map like this, or that kind of those kinds of things. And so you could afterwards on your own time, you can play with different displays of outputs this way and see if you have ideas, and then we can code up producing particular outputs for the uMngeni water model. So that's why I am going to skip sections 7.3.1, 2, and 3. I'll show you. Oops, I'll show you here. That are about bringing in multiple attributes and using the field calculator in GIS to do the difference between flow in and flow out, for example, to look at channel losses. Because it gives you flow in and flow out, but if you wanted to look at the difference between them, you could also plot that. But you can calculate that. They're having you calculate it either in the database program or in GIS attribute tables, which is fine, but I would do it outside of that. Again, using SQL editor again. And then this is also combining tables from two different types of outputs that are in, like you can combine things that are from the water balance output and the nutrient output into something together, or and do some querying. There's lots of things you could do, but I would not do them in this tool myself. And then again, comparing scenarios, you could do flow out for scenario 1 minus flow out for scenario 2 and plot the difference between them. So I'm just telling you what they're showing you so you know it is something you could do. But I wouldn't, the way that they do it here, I find quite clunky, so I am skipping that part. But you could, if you had two different scenarios, you can go in and do one minus the other one to plot the difference on a map. Like how much difference alien clearing might make, or how much difference controlling manure application on a pasture might make to the nitrogen or something like that. And you could do one scenario minus the other one and show where in the landscape are the differences going to be the biggest, or something like that. Then in this step, so I've skipped down now to step 7.4. And this is again just by printing to make images that you would save. So you can adding multiple to the display, and then it will save it. So for example, like in the tutorial, it shows you like this, when you go to that print step, you can add multiple maps, and then it makes a image file that you can save. So to do that, we would go to number of maps. Let's say, let's just do 2, for example, and you could put 2 of them in portrait. If I do this, is it gonna print? Okay, so then it is gonna do the ones that so if we had displayed, I just picked 2 and we've only looked at 2, so it does the 2 that we've made. If we had more, it would do, it would include whatever is in this results folder, the top. Like if I said, if we had made 5 of them and I said do 2, I think it does the top 2. You just have to change the order to show which ones it does. And it adds a scale bar and a legend and other nice things. How do I zoom? Yeah, so you can see it puts it on a layout view. For those of you who used ArcGIS or QGIS for this kind of thing, there's the interactive quantitative view over here, and then this is the display view for saving images of your maps with nice legends and stuff. But it does quite a nice job of the initial layout. Oops. And printing, and then you could choose to save this from the layout view. Also in different, you could export it as a PDF or an image, or otherwise. So that's what that print tool does. But I want to switch over to the animations because that's quite fun as something you can do with the output. So if I close, I'm gonna go ahead and close that, but that was step 7.4 in the PDF for if you're following along. So this is a static maps that we've been looking at. We're going to switch tabs now to animated maps. And we're now at 7.5 in the PDF. So they suggest for the tutorial to look at a channel-based one again. So this is outputs for the channel, and SDMorph monthly table. And again, if you need to know what's in those tables, you go to channel in the website. And that SDMorph is a naming holdover from, I think, sediment and morphology. And you can see all the outputs that are in it in that table on the website. But for this demonstration animation, we're going to work with the flow out again. So when you pick a table up here, you can, all the variables in that table are listed in this drop down. And if you don't understand what some of the abbreviations mean, that's where that table on the website comes in. So here we pick flow out. And you can see it's already added something in my project over here, default flow out for the animations tab. And then you can look at the attribute table already if you want, but you can do, I think we can just press play here, can we? Yeah. So yeah, you can just already go ahead and press play. So if it's already added it, so you can see what day it's on, September, it's monthly, so it's stepping through months, January 1994, February 1994. So it shows you here where you are, and you can see it's not much flow, not much flow, then it's raining and it's flowing and flowing, and you can pause. You can go back to the beginning. And you can also open the attribute table to see. Okay. It just shows the flow out. It doesn't show all the values. Okay, so they're being stored somewhere else. My windows went to the back. There we go. But it's quite fun because then you can also slide yourself to any particular, when you do it this way, you can slide through the dates yourself as well. So if I want to find, okay, where did it rain a lot? So remember, this catchment is quite an arid one. It's in Ethiopia. So the flows are quite low, and a lot of the time there's almost no water in it. So you see there's almost no water here. Very low flow. And then August 1993, there was a good flow. So low. And so on. So you can step through, and then you can also change the speed. So you play it at a certain speed, it steps through quite slowly. You can change the speed, make it faster. Especially if you had a long run, you might want to play with the speed. And then you can record, and it will record a little video of it stepping through. So you could choose the dates you want it to go through up here, and you can choose the speed you want it to go through. And you can actually make a little recording of that you could save and put into a presentation or show other people, which is nice. And then it's showing it in the map canvas. You could also show it in the print composer. So I stop and go back. And you could have multiple maps going at the same time, it looks like, probably from the, oh, okay, I think it just have different backgrounds if you had multiple of these backgrounds that show what's going on in the landscape units. So right now what's going on in the landscape unit, this is showing biomass, which doesn't have so much to do with the flow necessarily, but it could do if you picked multiple maps that you wanted to show it with, to look at them all together. You could do this. Okay, and so what's actually happening here too is that if I open this now, if I open the attribute table, let's look at this top channel. The flow is 5.21 to the -7, so super low. If I step my animation forward and then open the attribute table again, whoops. Okay. Step it forward here, okay. And then if I open the attribute table, it's a different value here now. So it is speaking to that database file in the results folder, and changing in every time step what is in this flow out. So if I stop it at any time period, it will have the flow out in this attribute table. That's how, and coloring it appropriately. So it's constantly changing that file and then showing it and changing it and showing it and changing it and showing it. To make a GIF of the animation, let's go back. I'm gonna go back to the map canvas view. If I click on start recording and I press, and it's gonna go through. I'll just stop it now, and then I stop recording, and we can see what we got. What does it look like? Okay, so it's written this as a GIF to our results folder in that default folder I showed you. I go, okay, and it's still playing because I didn't tell it to stop, so I said stop there. I stopped recording, but I didn't say stop up here. So if I say play recording, it's going to open up that file it's saved and play it for us in whatever Windows chooses to play GIFs. So I want to see what it looks like. There we go. Okay. So there it is as a GIF. And I think if you do it in that canvas view, it could have like a legend and other labeling you might want to put on it. So that's that animations tool. Does anybody have any questions about that? Otherwise, I'm going to move on to doing the plots. They've made it quite user-friendly, I think. It's just a question of working out what's in what table and what variables you would want to plot. People are okay with that. So that's the animation part. And then plots, this is just making normal graphs. Again, from the various tables that are available in the model's outputs. So you pick and I'll show you how to plot. You can plot the modeled versus observed, which is generally what we want to do when we want to check how well the model's doing. So, but it also allows you to do other kinds of plots. So it does line plots, and it also can do like box plots and other it can do flow accumulation curves, bar charts, and a few different things. So it is quite a nice tool in that way, and it lets you get an idea of things you might want to then like code up potentially so that we can do them more efficiently over and over. So the way the plotting tool works, we go over to, we're now at 7.6 in the tutorial PDF, and you go over to this plots tab here. And you have to first bring in the data that you want to plot. So there are all those many tables, and it will pull out the data for the different time step that you want and the different variables that you want. So, and then you can also save the resulting table that puts the different data together that you wanted as well into a CSV file that you could open in Excel as well. So that can be another way of pulling the data that you want out of the database file into a table. If you wanted to get it into Excel, you could also use this plotting tool to pull things out for you. So in the tutorial example, I want to select the data from the observed flow file that they've included for us as an example. So it says here, choose observed data file, and it could be observed what quality file, etc. But this one is an observed stream flow. So I copied all the example data into my project folder. So that's found in a folder called observed observed flow, and that was pre-prepared for the tutorial. Came with the software. So if I open that up, it has the file there now. And that file, they've formatted it in a way that matches the SWAT outputs to make it easy here. Oh, okay, sorry, this is still, okay. This is still speaking to this table. But this file is already formatted with the date and the flow in the same way. Actually, I could open it up and show you what this file looks like. If you wanted to use this tool for plotting, we'd want to put our gauge data into a file that has a similar format so that to use this plotting tool in particular. But it's, okay, so this is monthly. Okay, so this is monthly data, and it has a flow value, and it has headers, data, and flow, and it's a comma separated value. And you would need to make sure your units are the same as the model's units. So this is cubic meters per second average for the time step. So then we want to add the value that you would compare to it. So say SD monthly. Okay, so SD morph and SD monthly, SD have similar, they both have the flow out in it. This one has more in it. Flow in, flow out is all the way down here. So we pick flow out. It's a monthly time step. Our observed data is also a monthly time step. And then you would check a unit. Okay, so this unit is not units of the measurement. This is which channel unit this is for. So we have to, this observed data is for flow out of the end of the watershed, out of the end of the catchment. So we need to find which stream unit in our model is the outlet one. So it has them all numbered here. And the numbers skip some because I merged some, etc. So that's why it's 2, 4, 7, 10. That's how the channel numbers got stored. But you can't actually, because of the way the GIS links and everything works, the numbers aren't ordered from upstream to downstream, unfortunately. That would have been helpful. But I think because of all the branching and stuff, the numbering does get tricky. So you have to go to your GIS and work out what channel number is your outflow one. So in QGIS, this guy here is your select tool. So I would select, and it should highlight, maybe it's going to be easier if let me turn off some of this stuff and highlight the channel reaches. And I'm going to select one here. You can see it's yellow, the one I've selected. This is the outlet channel reach. And if I want to find out which one it is, I can open up my attribute table, and it's number 52 in my GIS. The thing is, it might be different in yours because I did some merging steps, and I think it's different in the tutorial because they did different merging steps in the example. So you'd need to go to your own GIS project and select the stream channel reach that is the outlet one. This last one, most downstream little piece of the channel, because we want the flow out of that one to compare to the observed gauge data, because their observed gauges down here. So for me, it's number 52 is the outlet. So you can see it's not the highest number, it's not the lowest number. It goes up to 87, and it starts at 2. So you do have to go in and check and then keep note of, in your project, what is the outlet channel number there. So you go and you check, unselect and zoom out, again, see my whole area. And if I come back here, I want to go and get 52. It's this one. So it's going to use channel unit, the flow out of channel unit 52. There are other ways of finding the identifier as well, actually, that the tutorial PDF shows you. You can also use this guy, the eye feature. I like selecting and looking at the table, but you can also yeah, go in and highlight with the information one. You have to, when you're using that too, you always have to make sure the shapefile you want to identify from is highlighted over in your menu over here. And then you can use this little eye, and then it'll give you a pop-up here, and you'll see it's channel 52. So then I'll close that guy for identify results. And then I go back to my hand or panning around the view in QGIS. So yeah, there's different ways of finding out the channel number, and the tutorial does mention some of those in the text. So now we have picked our unit and our variable. And we're gonna go to plot type. Oh, sorry, let me pull my window up again here. And we can go to plot type, and we'll do a graph to start. But there's other ones, so we do graph, and then we can click on plot. Oops, sorry. Add plot. Okay, there we go. We add plot. Okay, when we click plot, we have to, it tells us we can save the file as a CSV with the data that you could then use in Excel. So that's quite nice. And then it's going to put it loose in this scenarios folder, but I'm going to put it in our default folder. You can choose where you want to put it. You might want to put them elsewhere. So I'll say flow outlet. You could pick any name you want. I think in the tutorial they just say call it flow. And save. And then it's thinking about it. Okay. So right now it's just showing the modeled monthly flow. Is there? Okay. And then we want to, but we haven't added the observed data yet. I thought it would pull through, so we're going to add that over here. Go back to our, oops, I'm going to close this. Add the observed flow again. Huh. Oh, okay. So it says in the tutorial that we can, if we go add observed, there we go. There's the observed. Plot it. I'm gonna save it over here. Yes. Oops. Okay. So it says missing data, yes, for plot 2. So the observed data file has a missing month, and it talks about that in the tutorial. And because that's a thing that's likely to happen, you might have gaps in your data. So you can pick OK, and then you could change the finish year, or I think it will plot without it. And then let's see if I go OK. Oh no, okay, it doesn't want to plot without it. So they say These are reasons why I'd prefer to do this in Excel, for example, because then you can just skip those. Yeah, so sorry, in the previous, I skipped this button of adding the observed to our plot. And if you had other scenarios, you could add other elements to it by opening, you would open another scenario and you would open the other tables from it, and then add those or open the the tables from that output, because it tells you which scenario it's coming from, and then add them to the plot and plot them all together. So I've changed it now, as I suggest in the tutorial, to end in 1997 because there's a gap in the flow data. Oh, okay, so there's not just a hole, it actually stops. Apologies. The observed data. So if we do a plot now, find some data for some. Sorry, I messed up something by going back a step, but that's good because plot now. Row 2 isn't complete. All right. I'm going to start this over because, okay, by going backwards, I seem to have messed something up. So if I go back to our default and I go to our channel SD monthly and I go to graph bar chart, variable, I want flow out. Unit 52, gonna add it. Also want to add observed, change this to 97, let's try. And then I'm gonna save over this one. Yes, okay, there we go. I think going back and showing you that you could pick other tables, it wanted me to follow through on that, which I hadn't done. So now you can see the plot of the model output in the blue and the green line of the observed flow monthly. So you can see it often happens, like some parts of it are captured fairly well, like the low flows, but they're almost zero. The model does say those will be almost zero. And then some peaks are captured okay. This one happens late. When you see, or this one, sorry, the model, this one happens early, this blue versus the green, which is the observed. This one here in 96, 97, 96 is decent in terms of magnitude. This one here in 1993, the model is over simulating. And then actually over here in 97, the model is under simulating. So it's often tricky to, when you see it under and over simulating, if it's easier to know how to adjust the model if like it's simulating too much every time or too little every time. But if it's under in some instances and over in other instances, it can be that you can't fix it too much more than that because it might be about the rainfall data that you've used or some other element is not picking up those events the way they actually happened, because it's mixing over and under for the peaks. So we'll talk more about calibration another time, but this model's not doing too badly in that it gets some of them right, and then it's not systematically over or under necessarily. So it can be about the input data, and if you don't have any other input data, there's not much you can do about that from a rainfall point of view. There are things you could do, and so it gives you, what's nice is it gives you some statistics here too. It gives you an R squared, which is a correlation coefficient between these two, and it's 0.6 in this case. For people who know the Nash-Sutcliffe efficiency coefficient, that's also something. 0.5 is not bad. Yeah, so these stats, it's not wonderful, but it's not bad. It's pretty good. You would accept it for use in some instances. This is monthly again. So that's how you would do a plot, and you can save it. You can edit the axis parameters. You can make some subplots. You can pan around within the, you can zoom in and move yourself around in the graph with this guy. Go back through your views that you've used. Reset original view. And then, so you can zoom into specific spots and save those specific zooms as images. And you can also change the top to a bar chart, for example, and then you would click update. It would show it in a bar chart format, which for a monthly amount isn't too bad. You wouldn't really do that for daily data, but it depends what data you're plotting. So you could do, you can also do a scatter plot. And a scatter plot is going to be modeled on the x-axis and observed on the y-axis. And if it was if the model was perfect, all the dots would fall on a one-to-one line. So it plots the black line to show you how. So you see some dots are there's some over simulation and some under simulation, which is when it's down here below the line, over simulation when it's above the line. Oh yeah, it has the modeled is on the, apologies, model's on the x-axis and observed is on the y. So I misspoke. So here's when the observed is higher and the model's under simulating actually. Sorry, I said that the wrong way around the first time. So here's when the observed is higher than the modeled is, when it's above the line, not when the modeled is higher. This is when the observed is higher, the way that it's plotted. So I often plot it the other way around to the way that they've done it. So there's reasons why you might want to do it yourself if you like to see it the other way. But you can see there's lots of zero flow values in the model that are not actually zero flow values in the observed. So they're off of the zero axis in the observed, but they fall on zero for the modeled. So these are quite helpful plots you can look at. You can do a box plot as well. So that will do the mean and the outliers of all the monthly flows. So here you can see that the mean modeled is lower than the observed. The distribution is also sits a bit lower than the observed. There's outliers in both cases, or like the edges of the distribution are here if you know box plots. So it's nice, this tool, you can do all these different plot types. And if you had multiple scenarios, or you could add those on when we set up the importing of the data to the plot. You could add, and you could also plot other model outputs. We were just plotting flow here, but you could plot nitrogen in the channel. You could plot like aquifer outflow from the groundwater, and you could plot multiple things on the same axes here if you wanted to. And on the same graph, but it would make a secondary axis. For those other units if you wanted to. The other one, does it show flow? Oh yeah, flow duration curve is also good. Let's just look at that one. This is a nice one to look at too. This is a good illustration as well for when you're looking at sort of, are the highs too high or the lows too low, more systematically. So as you can see, here are the high flows that are, some of you might be familiar with looking at this type of graph, but this is exceedance percentages at the bottom. So for 20%, only 20% of the time would the flow be greater than this amount. That means the high flows are down here in the low percentages. So like the 10% of highest flows are over here. And then this means that the flow is at this amount, like the 50% here would be the median, and the flows are lower than that 50% of the time and higher than that 50% of the time. So it's about frequency of occurrence. So these flows happen very rarely, and these flows that are greater than this happen often. So what you can see is that the low flows are fitting well, and then the observed and the modeled in these sort of middle high flows, the observed is higher, but then the highest flows, the model is higher. So that's a bit tricky to fix from a calibration point when they cross over like that. Sometimes there's not that much you can fix. Or as I said, if it clearly deviates where the modeled gets much higher than the observed as the flows get higher and higher, or it gets much lower than the observed through this part, or in the low flows, it's more straightforward. So this model has already been somewhat calibrated to this observed data as best they could. And this might be one of the best, like this might be as good as you can get the fit given the setup of the model. But this flow duration curve is quite a nice one to look at your distribution of high and low flows. Yeah, so that's the plotting tool. Again, you can save these plots. Oh, nice. Yeah, it also gives you some statistics down here when you do the flow duration curve. It gives you the observed min, max, median, first quartile and third quartile, which will be like the 75% and the 25% values. And it gives you the modeled min, max, median, first quartile. So the quartile one, that's the 25%, or the 75% exceedance over here. So you can see the modeled is 0 and the observed is 0.3, and then the 25% over here. Over here is the modeled is 3.34, and the observed is 0.48. It's higher. So it gives you some statistics down here that are quite nice to look at too. And then you could save it as a PNG, which is an image file format. I think that's the only, oh, okay. You could also save it, okay, they give you a few options. You could save it in these other PDF or a JPEG as well. Okay, nice. So you can save it in a few different image formats if you want to. And for different zooms, etc. And then when you're done, new file to plot. Oh, this would be adding a new. So when we brought in the data, it had us save that CSV file that different. If we had a different version of it that we wanted that we'd saved as a CSV, we could pick it here. But we only have this one, so there's not a new file to plot. And then we'll close that. But if we could add some more things to plot from different scenarios here. So we've gone through, we've gone through everything in the tutorial that I wanted to go through in terms of plotting and visualizing outputs. But I do encourage you to play around with this output tool with your tutorial model on your own time at some point, just to get a feel of what are, and start thinking about what are different kinds of things you might want to plot and you might want to look at, and what do the outputs look like? How could you show them? Thinking for the uMngeni system. So before I close this, does anybody have any questions on this part, on these visualization tools, plotting, making maps, plotting outputs, making little animations? Correct. That's quite clear. So again, we've gone through section 7, most of it. We skipped a few bits in the tutorial here. So what I'm going to do is shift gears for the last half hour and look at some of the inputs for the uMngeni model just to get us thinking for next year, because we're going to take a break until likely until February. We'll be in touch about when to do those next sessions, and then I will go through the uMngeni water model as it stands in more detail, and we can discuss different bits. But I think the land cover, let me close this and close this, is one of the most important things to think about. Because as you saw, when we set up a model, we put in the land cover map at the beginning and all the structures based off of that. So you want to get that the way you want it before you start doing other things. Because otherwise you have to go back and restart the setup of the model, delineating the HRUs, etc. So it is important to get it right and get it the way you want it as the outset. Otherwise, it's quite a lot of work to redo everything to put in a new one. So I will save this guy, and it always gives you this warning to say that you're working in multiple softwares, and I say okay, and I can close that. And it closes down the SWAT one. So I'm going to switch gears. I'm going to get my presentation back there. So I'm going to give you an overview of the model of the uMngeni water catchment areas that I worked on previously, and I'm transporting into SWAT Plus now, and the inputs that were used. And then we can talk about in the land cover in particular. So just to recap, we need the rainfall input and the evaporative demand. We need these catchment properties that come from the DEM, like size and slope and the channel network, and then the land cover map that we need to prepare and the properties of each land cover type, soil types and the properties of those soil types, the aquifer properties that we want to assign, and any properties of the channel network, also in terms of like point sources, in terms of sizes and how things get processed within the channel network. But then under the anthropogenic activities and systems in the catchment, we need like water transfers and point sources, withdrawals, transfers of water, storages of the storage dams, and the rules of the inflows and outflows, irrigation settings, fertilizer settings, any manure application as well, harvesting of crops, and then any special things we want to represent about the urban systems. So the impervious area connectivity is a key one, and then some of the pollutant wash-off stuff we can add. So all of that goes into making that model structure we have and setting the parameter values for the HRUs based on their land covers, and setting parameters for the aquifers based on their geology, and the channels and the reservoirs. So we go through that structure of building stream network subcatchments, HRUs based on cover and soil, and aquifers based on landscape units. So what was done for the uThukela water catchment areas, you'll see a map of that. When I delineated for the previous version of the model, there were 163 subcatchments. The points for the subcatchment delineations were selected with a few things in mind. Where there was some flow data, where there were gauges, where there was some water quality monitoring points, where there were reservoir outflows, and where quaternary catchment boundaries are as well, so that we can line up with those, because sometimes there's other data at the quaternary catchment level. And so that could be revisited if there's any big new water quality modeling. I see somebody else is sharing their screen. Is that me doing something? Oh, so Musile, I think you're sharing your screen somehow. Are you guys still seeing my screen? Okay. So the climate data that was input before, I used a mixture of HydroNet for the precipitation. And I used ERA 5, which I'll talk more about another day for it's a reanalysis climate product that I used for the temperature and wind speed, etc. Products, inputs, pardon me. The HydroNet's precipitation, I also extended it a bit using CHIRP's data that I bias corrected. Now, I don't, Tando mentioned this morning that there's a feeling that the HydroNet data I did not bias correct the HydroNet data at all. So that's, if we need to do that from now, we can look at how to do that in this next iteration of the model, and I'll ask Jason what he's looked at there so far. I know that CHIRPS, for example, is a satellite product that does definitely need bias correction because it's I think it overdoes the low rainfall amounts. The land cover map is what we'll talk about more now, but I reclassified using the national land cover mapping from 2020. And we'll talk about that, what that means in a sec. And then I had to assign properties to those vegetation types, and we looked at that. There's SWAT comes with that database of parameters for lots of different crop and vegetation types. So I used those, but I also modified some of them. I looked at the ACRU database on
Sorry,
different
Julia.
vegetation types. Yes, hi.
Apologies. I think when I had that sharing by mistake, it affected your projection. So you're not showing anything now. I'm not sure if
Okay.
you have any slides on. Yes.
Oh yeah, I do have slides on. Okay. I didn't notice. Okay, apologies. Okay. Let me go back. I'm not sure. Was I on this slide? Yeah, when I stopped. Okay. So I still stayed on the slide. I was just working through the points there. So I'd use the national land cover mapping, and then for the soils, I'd use the Agricultural Research Council has a land types database, and there was a project from the University of the Free State and University of Pretoria where they were assigning SWATs. They were making a SWAT soils properties database linked to the ARC land types database. So I tried using that. I had to modify things a lot. It didn't work that well. So I actually want to revisit the soils in this round. What I'm getting now is there's a project that people at UKZN did actually for ACRU to assign soils for different topographic units within the land type units. So I don't know if has anybody here used the ARC land type data before? Does anybody here work with soils data for your areas? But if anybody does work with soils data, and you have any ideas of other data sets to look at for this area, besides these national ones, please do let me know. Soils data is always a tricky one to find unless somebody's done a really. There'll be detailed soils maps for small sub areas, but generally not for the whole area you want to work with, and we need something that covers the whole area. But gonna see if the new one that UKZN has made for using topographic units within the land type units works better. So I'm actually, they sent me that data today, so I'll only be able to show it to you next time because I haven't processed it and made maps and stuff. But then aquifer properties by subcatchment, I used the geology. You can get geology map GIS layers from Council for Geosciences. There's a free version has sufficient detail for what we want to do. They have finer versions if you're wanting to like sink a local borehole or something that you would have to pay for, but for our purposes, the level that the free one is fine. And then there's some properties of aquifers that were generated through the National Groundwater Assessment too, which it's an older report, it's early 2000s, but it has some of the values that we need for SWAT in terms of the recession coefficient estimates and like porosity of the aquifers. And then the dams and their dimensions and their outflows, I got data from DWS and from uMngeni Water, and I had to patch some of the time series. So some of the dams have pipe flows out and pump flows out, and then there's controlled releases. So I needed to give daily time series for those for the different reservoirs in the system. And then point source flows and water quality, again, the data was from uMngeni Water, but when there were gaps, I had to make some assumptions, either that, was the flow this similar to other similar months, or was it off? So I had to make some assumptions to patch gaps in data for points, or did that point source not exist earlier? You can add things that start at different times. So for the wastewater treatment work outflows. So to go more into, so we'll go through these things one by one starting next year and what the specific inputs were and how to, if we want to change them. But to start thinking through is the land cover. So I used the National Land Cover dataset, as I mentioned, and at the time, the most recent one was 2020. They've released 2022 now. So it seems like they're starting to release them every 2 years from going on. And when you're modeling, land cover is changing over time, but in our model, we're pretending it's staying the same. There are some functions in SWAT to change it over time, but it gets quite messy and complicated. And so different ways of doing it, you can set up separate models for different time periods that have different land cover maps as inputs if you think things changed a lot. You can do that switching. The reason why it gets messy is because you'll remember how the HRU delineation worked. We input a land cover map, and that land cover map is used to make the spatial units in the model. So if you want things to change, they're going to change within those same units that were delineated based on the land cover map. So you could say certain specific units change from one land cover to another, but you have to have those be a separate class from the outset so that they are separate spatial units in the model. And so it does get quite messy to do that. So we generally try and find time periods where land cover is relatively constant over time periods like 5 years, or more or less at a larger spatial scale. When you start modeling like 50 years or longer, or even 30 years, you start seeing more substantial changes. You need to think about how to handle that. The HydroNet climate data that we've been talking about using for this project really only starts in 2020. So we're looking at modeling 2020 through 2025 for this iteration. And so if we do that, we probably want to use the land cover map that sits in the middle of that time period. So switch over to using the 2022 one. But it is something to consider that one might want to then update it over time as new maps come out, if there have been big changes that it's important for your management considerations to have those represented in the model. Has anyone in this group, has anybody looked at or ever used the National Land Cover mapping data before? Even in coursework when you were studying, has anybody used it or downloaded it ever before? Seeing. Any hands? Do you have land cover maps that you're using in your own GIS for uMngeni water?
Yes, Julia, we normally use the current version, the 22 one, but
Okay.
we've used the previous versions.
Okay, so you are using this data set. Okay.
Yes, we are.
Great. Great. And when do you do any reclassification of it? Do you use it as it is?
Normally for us, we use them when we just doing our baseline catchment assessments. So we do not normally do a lot of classification.
Well, I'll show you why we might want it, why we would consider doing reclassification for this model in particular, and then it's something to think about. So for people who haven't used it much before, when you download it, it comes with, there's 73 classes. Well, there's actually a 74th that just says no class, but I think there's none of that area here where they weren't able to classify it for one reason or another. But there's the highest level of classification, the most detailed one has 73 classes, and you can see a section of it there. Obviously, I've just cut it off, and then there are larger lumped classes. So there's a 9-class set, and there's a 24-class set, and then the full classification, the full level of detail is the 73. So the 9-class one has barren, built up, cultivated, forested, grassland, shrubland, water bodies, and wetlands. So that's quite broad, as you can see. And then you get into 24 types, where it's broken down into consolidated, unconsolidated for the barren. And then sort of, I think that's talking about the material of the barren land, how permeable is it likely to be? So like consolidated dry pans and rock surfaces that won't have many fractures in them. And then unconsolidated is like sand, like more porous stuff. So river sand, coastal sand, eroded lands, other bare soil rather than rock. So that would be, and then there's these levels of built up, commercial, industrial, residential, small holding, transport, urban, vegetation. So yeah, vegetation versus commercial and industrial. So parks, and then village would be a sparse, another level of village dense. It's not always clear to me, village versus small holdings and low, but we can look at it like what that means in terms of impervious vegetation surfaces and not. And then there is cultivated land. They break it up into temporary, permanent, fallow. And then as you get into, you can see it breaks it up into many more different classes of, in the 73, like bare, bush, grass, the structure of the vegetation. Is it trees? Is it low vegetation and crops? So you can see, and then forested land gets broken up into planted, so tree plantations versus non-planted, and grasslands. So there's some useful classes. And then if you go all the way to the 73 classes, there's useful classes in here. The crops get broken up into some crop types. The particular ones are orchards, pineapples, vines, and sugarcane. And then the rest are non-specific types. And so the classifications are nice, but they don't, for modeling and SWAT, they don't meet all of our needs quite easily enough in terms of separating some cover types that might have different hydrological and water quality impacts that we might want to look at individually, and you might want to model with scenarios. In particular, is separating out crop types, and another one is invasive alien vegetation. With the alien vegetation in the previous model, I didn't separate that out. the national land cover map, it does separate out plantations of pines and eucalyptus, but it doesn't separate out areas where it's just invaded and spread on its own. It'll show that it's woody cover, but it won't show if it's indigenous or non-indigenous woody cover there. So I just left that out. There are other maps around produced by other people that classify things into invasive alien vegetation using different methods. So we could look at merging something like that if it seems important for your modeling, if like looking at alien clearing is something that you're going to be particularly working with here. Because the focus was water quality and stuff in my original brief, I didn't put a lot of effort into trying to find invasive area maps beyond, like the national land cover, as I said, does cover actual commercial pine plantations and eucalyptus plantations, but not invasive spread. So if that's something we do want to include in this modeling, we'd need to look at where to get the delineation of that. The other thing is crop types. I made some assumptions about crop type. I had to make some assumptions about crop types. Let me just pull up can you see my Excel? I've taken over the window there with the Excel file. In terms of crop types in the 73 class, you can see that there are, as I mentioned, there's sugarcane, and that's helpful to differentiate. But then in terms of temporary and subsistence, subsistence small-scale annual crops, it doesn't say what those are. And then there's rain-fed and pivot irrigated and non-pivot irrigated. And then there's also pasture lands that get classified. I'll go into, we'll look at that in more detail when we come back next year, just looking at the time. But to think about these classes of agriculture and how we might want to group them and subdivide them to represent in the model that have different applications of fertilizer or not, different irrigation or not. The irrigation or not is covered in the national land cover mapping, so that's very helpful. But then it's whether, you know, what are some of these types? Is it maize? Is it other vegetables? So I made some assumptions about things being a mix of vegetable crops and that's the subsistence crop. I just modeled it all as maize, for example. So if people have other information on this or that we want to bring to bear, we can look at how to reclassify some of these types. And I did condense, I know we're about to end, but I'll show you, I did condense the types into 19 different classes rather than, so there's 73 classes and in the map for the whole country, but within our catchment areas, there were 54 classes present and 37 of them had significant coverage, like you might want to model them. But it's still a lot of classes in terms of how fast the model can run, and the number of parameter values that need to be input and assessed. So I did lump some of the classes into like the grasslands and the woodland classes and things that I didn't think we're going to have such a huge impact on the water quality part that we would want to represent them separately. But we can revisit that, and then also had to group some of these residential classes, but we can come back and ungroup them again if we want to. It's always a balance of making a model that's not going to take hours to run. With my 19 classes to run, it would take about half an hour, I think, to run for a 20-year run. No, it's more like 45 minutes, yeah. So, which is not too bad, but when you're trying to fix things, you change something and then you wait 45 minutes to see if it worked. that's really not bad at all. But if we add more classes, it will make it slower and slower than that. So there's always a trade-off. You want to pick what you need to represent for your management questions, obviously. But then things that are not critical to your management questions, is it reasonable to lump them to some degree? So that's something to think about. And for those of you who work with the national land cover maps, have a look at see those classes and see if and the areas that you're working in can have a think about how we want to break these classes up and come up with something that's derived directly from the national land cover maps, but it has a reclassification set that is easy to just reapply every time they come out with a new map. Yeah, so that is all that I had to present today, and I see it. We've hit 12. But this is just to prime you to think about these things. And I will be sending you this presentation, so you'll have all of that. And then when we start meeting again next year, we'll start going into these in more detail, the exact climate inputs and land cover input, soils, etc. And then we will look at the output processing that you want to do for your, the management questions and scenarios and things you want to look at. How should we code up some of that output processing? So yeah, we've I don't want to keep you late. Sorry, I see it's just gone over 12. But if you have time, keep looking at that background document and playing with the tutorial model, because I think it's a nice way to, it's a small model you can play with without it taking so long to run and load and stuff. And keep thinking about how you might want to, how you would build a model for the areas you're working in, particularly the land cover. We've talked a bit about the climate data as well, and soils, if you have any more soils information. Before I don't want to keep you, but if anybody does anybody have any pressing questions or comments before we close out? Cool. Well, do feel free to see a thumbs up. Do feel free to email me if you need to, and then we'll get back to you with when the sessions will happen in February. And I will put the videos up. I have a backlog. I did say I'll make edited versions where I take out gaps and ums and mistakes and stuff like that to make it shorter if you ever need to rewatch them. So I will be doing that now that I have more of a gap for the break. So those will be up, but probably only mid-January, I'd say. But then you have them for future if you ever need them. They'll have a shorter version to use. But for now, I've just been putting up the full ones for sake of time. I see somebody's typing. Glenda, feel free to speak if you'd like. Oh, thank you very much. Oh, I see your speaker not working. Great. Thank you. Yeah, so I hope you all have a good holiday season and get a break and have a good rest. Thanks, everyone. We'll chat more next year.
Thanks, Julian.
Thank you, Julia. Bye.
Bye.